So as we've seen, every application has a scalability limit. Now, where does this limit come from? Well, Amdahl's law gives us a simplified way of thinking about the fundamental limits of scalability for a parallel application. And Amdahl proposed the following. He said, suppose you have an application that constitutes this amount of work, and for simplicity, we'll call this one time unit. So you can think of this as an application that takes 1 hour to execute from beginning to end. Now, what Amdahl observed is that for any application, it's always the case that there's some part of that application that can be parallelized and some part that cannot. And maybe that part that cannot be parallelized is setting up the I/O. Maybe it's organizing the parallel part. But whatever it is, every program has some fraction that cannot be parallelized. So I'm going to divide this program into 2 parts. This part P is parallelizable, and this part S has to be sequential. And so we'll use S to represent the time for S to run, and P for the time that P would run if we did it on one processor. Now we can kind of think about Amdahl's law graphically, which is to say, suppose I took this application and I tried to run it on 2 cores. Well, if I did, I could graph the application in the following way. I could say, first we have to do the part that is sequential no matter what. And then we're going to take this parallelizable part, break it into 2 pieces, and then run them simultaneously. And so then the runtime for the whole thing is something a little more than 1/2 of one time unit. If I go a step further and say, now let's run it on 3 processors, then I would have something like this. The sequential part followed by 1/3 of P, and each 1/3 of P runs simultaneously. And again, the whole thing runs faster, but as we divide it into smaller and smaller pieces, our benefit becomes less and less. All right, so the way we can think of this is that the runtime for a given application on n cores is going to be the sequential part plus the parallel part divided by our n cores. And that makes sense because we have to do this part and then we can divide that part up. Now from last time, you'll remember that the speed up is going to be defined as the time to run on 1 core divided by the time to run on n cores. And since we define this to have 1 time unit, we put n in the numerator and then S plus P over n in the denominator. All right, so if that's a correct model of our application, then this is going to predict the runtime and the speedup. Now, Amdahl's law is a law in the sense that it predicts the most important behavior of an application. It's not meant to be a detailed model of any specific application, but it's meant to describe the behavior of an application in the limits. And so now the interesting question is to say, what happens if we take n and extend it out to infinity of the speedup? Well, if we do that, this n here is going to cause that term to go to 0. And so our speedup in the limit is always going to be 1 over s. So if, for example, s is 1% of my entire application, then the max speedup I could possibly get is going to be 100 times. Now, Amdahl's law describes in coarse terms any parallel application. And so it's telling you that no application can scale out to infinity. There's always some component of it which cannot be parallelized. And that means there's a limit to the number of processors on which you can run and still get a benefit.